So hello, virtual attendees. We're about to talking about how to run RMG jobs, and we'll start walking through several important blocks in the input file. So the general procedure for running RMG, as you can see, like the other line here. So basically, you have tried before. You will put first -JL and then specify the task for the program to look at where to execute the RMG.py, and then you can put some optional arguments. And you will also specify the input file. And you can put the export task for the RMG.py on your .-rc file for Linux user, and for Mac user, you will either be using .-rc underscore profile or zshrc. So then after doing this, then you can just directly specify the RMG.py instead of like putting this a specified tab to look at. And the output files will be placed in the same directory as your input file by default. So some notes about the conduct. So from the new style, which is introduced in version 4.4. So if your terminal prompt looks like this, so there's a parentheses, that base, then you should use the conduct activate RMG environment. And for the old style, you'll just use the source activate. And if you're using the Docker, yeah, you can run the commands from the RMG website, which will also help you to activate the RMG environment. So there are some optional arguments, and as you have tried before, you can put the --help argument, and then you can see all the possible optional arguments listed there. And one of them is to specify the maximum runtime. You can use the -t or --wartime argument here, and it will go with the days, hours, minutes, and seconds. So then you can, yeah. So this example is basically means the maximum runtime will be 1 day.
And is the leading 0 on 01 required?
Yes.
You have to do 2 digits for the days.
Right.
Okay.
Or yeah. And if you want to run a parallel, then you will use the -n to specify the number of processors you're using. And yeah, if you're interested in running parallel, you can go to the RMG website. So for RMG input files, the documentation, you can look either from the RMG website, this here, or you can go to the RMG.py/examples/RMG. And if you remember previously, you will go to the super minimal folder, but now you can turn to go to the commented folder. And if you look, you open the input file there will be a very detailed explanation for several of the input attributes, the input specifications. And you can also look for the and many other examples located in the RMG folder. So our first goal is the database specification. As you can see, there are several libraries you can specify. The first one is the thermal libraries. So you can basically list the libraries of thermodynamic parameters in the order of how trusted they are. So here is the example of putting the primary thermal library, and you can specify multiple of each. And the order, the first, that means you trust the parameters in there, in that library the more. And same thing applies for the reaction libraries. So it's the list of libraries of reactions and the associated rate parameters to add to the model H in the order of trust. So if you include the reaction library in the reaction libraries, those reactions will be first added to H. And after the RMG simulation, if all the species has been detected as like high enough flux, then there will be those reactions will be moved to core. But that doesn't mean at the initial point that will be moved. But if you look at the third one, the sleep mechanisms, it is also the list of library of reactions and the associated rate parameters, but that would be directly added to the model core initially. So you can choose which case applies to you most. And for the kinetics depositories, generally you can just set it to the default. And for the kinetics families, it's a list of the reaction families considered in your interested kinetics systems. So usually default is okay. And for now that the whole RMG has in total about 74 reaction families. And the default, I just checked it, it has about 50-ish reaction families included. And you can, if you're interested in, you can also look at so there is a recommend.py located in the RMG database, and you can look at it to see if like there are some like different recommended reaction families that you can use in your case. So for example, there is a CH pyrolysis system. So if you're interested in constructing kinetics model for CH system and pyrolysis, then you can use instead of use default, use the CH pyrolysis.
Yeah, but if I have multiple families to consider it, like, should I put a comma and the others with?
Yes.
Okay.
Yeah. So for example, for my case, I'll usually put the H abstraction and radical recombination, and then whatever reaction family you are interested, you can just add it.
Okay.
Yes. And for the kinetics estimator, the method we use to estimate the kinetics, usually you can just set it as the rate growth as it is. And for the species specification in the input file, basically all different species are placed in the model core at the initialization. And if you mark it as reactive, the default is true, but you can also specify it's not reactive. So you mark it as false, and then no reactions will be generated for that species. Usually this will be used as for some inert gas like helium or argon. And you can also define the species either using the INCHI, SMILES, or adjacent base.
Quick question. So if it's inert, like, you mentioned helium and argon, should it just not find any reactions regardless, even if you set it? So is this just to like save some computations because you know it beforehand?
Right.
Okay.
Right. So sometimes for example, your system would be like more than like 92% of helium and only 8% of the species you're interested in. Then you can specify helium. And then for the simple reactor, so in every RMG info file, at least one reactor must be specified. And the temperature, pressure, and initial molar fraction are required to specify as well. Also, you can see the termination conversion and termination time and termination ratio here. So at least one of the termination criteria must be specified. So this defines the endpoint of the reactor simulation, not the RMG kinetics model simulation. So usually you would, as if you remember what Bill just said in his introduction. So RMG during the model generation part, it would keeps to simulate the reactor until some time point or like the reactant conversion. And then it will pick what's the important species and the reactions be moved from age to core. And this procedure will just keep going until you think all the species in the age is like their concentration is not high enough.
So for the temperature, it says 700 Kelvin. Does this mean that we have a reactor at 700 Kelvin and we're just inputting the stream at 700 Kelvin? Right?
So for the simple reactor in RMG, it means it's homogeneous gas reactor and it's closed system.
So if the reactions are happening or the RMG is calculating or the mechanism at 700 Kelvin, and if we go on to use the same mechanism in Cantera file, in for example, a PL file, and I want to run the reactor at 500 Kelvin, how does RMG ensures that the mechanism, if calculated at 700 Kelvin, would still work at a reactor at 500?
Okay, that's a good point. So actually I think let me make sure. Yeah, so this is the next slide. So you can also specify a range of temperature, pressure, and the molar fraction. Yeah, so in your case, if you want to both simulate at 500K and 700K, then you can use the range settings to make sure that RNG will like randomly sample between the range you specified, and the mechanism will basically cover all the important chemistries in like from 500K to 700K. But finally, you will only get one final model.
Yes, one final. So in case if I have an input file where I have just specified one temperature, and if I go on to use the mechanism in a Cantera file with a different temperature, it's not a very good build-up, right?
I think it depends if your system is very sensitive. So for my case, I usually like I will just run simulation at run model generation at temperature about 700K, but I'll also like run Cantera simulation at slightly 650K ish, and I think it works fine for my system. Yeah, but it's also like better to like clearly specify and try to cover all the important species and reactions from the model generation.
Thank you. And one more quick question. So I see with ethane also there's a range of mole fraction. Would RMG automatically change the mole fraction of N2 and O2 to make it like a one mole fraction?
Right. So that's also a good question. So you can see the balanced species here. Yeah, so that is like you can specify the species to adjust the molar fraction of that species for balancing the requested molar fraction range. Yeah. Otherwise, like they will just automatically recalculate to renormalize to one. Let me go back. Right. So one key point is that at least one termination criteria must be specified. And you can also like specify 2 or 3 of them. So here there's another parameter, the N sims. It's the number of simulations at different conditions, which must be finished before the RMG simulation can be terminated. So that's basically help you to avoid that situation that, oh, at this temperature condition, I just simulate like for 2 times, and then I think that the model is good, and then just.
So does NSIMS override termination time in that regard? Like if you need more time to run 10 simulations, would it override the termination time stopping criteria? Or which one like gets priority over which one?
So I think the termination time is the thing that tells you when should I end this time of the simulation, this turn. Yeah,
Oh,
but the
so that's for-
NSIMS is like how many
Okay, I see.
simulations,
So termination time is for one simulation, NSIMS is number.
right?
Okay.
So since you have 10 sims specified there over a temperature range, would it just do? Well, say there was only 1 bar pressure, there wasn't 10, and you still had 700 to 1100 Kelvin. Would it just split that difference into 10 different temperatures and run simulations at all of those, or is it? How does it determine like?
Right.
Yeah.
So, because here you specify like different range, and RMG will, it will somehow try to I would say evenly try to cover the overall range that you specify. So it will like at each, temper. I should say maybe like, for example, it would, have like a simulation at 800K and under 5 bar. So at this specified condition, it will try to simulate at least for 10 times. Yeah,
So is there a way to, I guess, while you're using the range feature to say, I wanted to go like calculate over this, like specific temperature conditions, or do you just use the simple reactor and you'll just have to manually run it each time at say 700 Kelvin 1 bar, and then again at like 900 Kelvin 1 bar? Instead of it being like a random picking random places, is there a way to specify exactly which ones you want while
yeah,
using this?
yeah. If you want to like exactly specify the condition, my recommendation would be you can have separate input file. Yeah.
Also, another quick question. Is there a reason why the sensitivity analysis is not done to like figure out like what like the next temperature to simulate should be, and why would it be random over like using some sort of sensitivity to like better predict the next important temperature or something, is there something like that in the code at this point?
I think one of the reasons could be running sensitivity analysis is like usually you will have one finished mechanism, and then you run the sensitivity analysis to figure out what's the like really sensitive reactions and species. Yeah. And another thing could be like running sensitivity analysis is usually pretty expensive.
Even the adjoint one, like the new one that Matt got, is that not like fast enough that it could justify the use here?
Yeah, I think that's a good point. I think maybe in future the RMG fully use RMS, then we can try to switch to that.
Okay. Thanks.
So instead of using this, so previously the simple reactor is the gas reactor, and now RMG can also support the liquid reactor. So the thing is that you have to specify the temperature, the initial concentrations, and you can also specify the constant species. So which could be a list of the species should have the constant concentration during the simulation.
The concentrations are more mass based or volume based. The concentration for liquids, or yeah, but what units for concentrate? Like what are the units for the initial concentrations?
I think it's Yeah, that's a good question. Has anyone used liquid reactor before? Because from my guess, yeah, I think I have to check the liquid reactor specification because from gas it's constant TP, so the volume will be varying. And for liquid reactor,
Yeah, I was wondering because I remember
Small
the
fraction.
small fraction. Okay. Okay, sounds good.
Why not add it to one?
It will normalize it.
Oh,
for you.
okay.
Okay, good. Small fraction. Okay, good.
and a solvent must also be specified using the separate solvent block, which is shown at the third bottom here. So if you're looking for a list of the solvents that are supported by RMG, you can go to the RMG website to look for the list of solvents. So previously, I have briefly introduced the 3 termination criteria. So the termination time, which can always simulate to a specific time, but we usually don't know how long the reaction will take. So it's not good to simulate too far after like most of the chemistry has been ended. But it's good to choose if the input species has the radical. And you can also look at the termination conversion. So often we have some idea about what the value is. For example, like you can terminate when the conversion is reached 80 or 90%. But intermediate models may not reach that conversion. So mostly it will be at the initial stage and may terminate early before all the chemistry finishes. And for the third one, the termination rate ratio, it will terminate when the characteristic rate reaches a given fraction of the maximum corrective rate observed so far. So you'll be very cautious when you're doing this, choosing this.
How do you define the characteristic?
So that's RMG, it will calculate the like all the species concentration and then I think it's somehow summarizing in a way.
Because so there's multiple reaction and this is somehow like a summary of all those reaction rates or something like that.
Yeah, I would say it's like the characteristic rate would be of flux that's describing the current overall system.
Okay.
Yeah, and if like any audience is interested in like knowing what's the characteristic rate, you can look for the Gauss 2016 paper.
Okay.
And then we will go to the model and simulator parameters sections. So these are really important tolerance that you usually will tune. The tolerance move to core is the criteria for selecting the species. So on the smaller value, you will finally get a larger core model. And for the tolerance keeping age, it's the criteria for flux pruning. And if you're interested in knowing what pruning is, you can go to the RMG website, or like I believe we have the advanced sections on the state. So the smaller the value is, you will get the larger age. And usually the default setting is for the tolerance keeping age is 0. So for the tolerance interrupt simulation, it's the threshold for stopping the simulation before reaching the termination criteria. So the lower the values, it will improve the speed because like I can show the slides here. So this is an simple example. So the tolerance multiple is the blue dashed lines here. And the A, B, and C's are like different species concentration during the simulation. And the tolerance interrupt the simulation should be always higher than the tolerance moved core. Okay, so suppose we run this set of the simulation, and then you can see the species A, its maximum flux exceeded the tolerance moved core. So in this run, we'll think, oh, species A is really important. We should move it from H to core. So then A will be moved to core. And for B, it will also be being included from H to core. But like, as you can see, if we set the tolerance interrupt simulation at this point, so that means the reactor simulation will not go further than this point. Vertical line here and here. That means it can save you the rest effort and resources and time from simulating further from this point. And for the tolerance keeping age here, it means if you look at species C, because its flux is all the way below this threshold, then species C will just be pruned. That means it will be removed from age.
I had a quick question. So let's say if I'm running a simulation and then, this is probably at the early stages when I'm adding quite a few things to the core. So if, let's say case B is true, it means that after basically the React, it would stop it, like for every iteration, I would have only like one species adding to the core and then restarting simulation, and then wouldn't it might be better to like finish one run, maybe add 10 of them and then kind of go from there?
Yeah. So that's also a good one. So by default, you will at each simulation, you will only move one species from each core. But the thing you're mentioning is also doable. So that's additional. I'm not sure if I included in this slide or in. Okay. Yeah, so there's another parameter called like species, number of species per iteration. Yeah, and like if you change it to 5, that means every simulation you will move the 5 highest flux species from H to core. And for the filter reactions here, that means you will generate reactions between species only after their concentration has a threshold. And for the reactor reaction filter reactions, I believe we have 3 arrays. The first one is the unimolecular, and then we also have the bimolecular, and for the bimolecular as well. So that is basically a mask. Tell you like, oh, for this species, we can like keep going to estimate the concentration and the rate. And for some other like really small concentration species, then we will just have put the mask of false. And that means like in the future RMG runs, we'll never think about like try to map this species to any of the reaction template. And for this filter reactions, our recommendation is like you always try to turn it on to a little bit speed up for your model generation. And for the simulator sections here, it's about the absolute tolerance and the relative tolerance for the ODE solver. So usually our recommend is try to leave it as the default value unless you have some solver issue and then change it to a smaller number. And for the sensitivity tolerance, which are optional, and it will not be used unless you're running a sensitivity analysis. So for the miscellaneous options sections here, the first one is the generate state for each iteration. So this, if you set this to be true, it will create the libraries of the core and page after each iteration during your job run, which can be used to restart the job if it fails somehow or at some point. So if you think you might have the need to restart the job, we suggest you to set this to be true. And for the save simulation profiles, it will save the concentration profiles for each simulation that RMG runs, which will help you to further diagnose this if there is some issue that you have during your RMG job. And for the generate output HTML, it will generate HTML files for better visualizing the model in each iteration, and can be expensive for large models. So only turn this to be true if your model is within a smaller size. And for the save age species, you will only need it if you're interested in looking at what is formed in the age. And usually from my experience, it could be very, very large for the folder size, for the file size, for large models. And for the verbose comments, it will save the full comments for how the kinetics rate row averages are obtained or calculated, and can result in very large campaign files. So yeah, you always have the option to turn it on. And we have additional block for pressure dependence. And for pressure dependence, it's usually important for small molecules systems running at high temperatures and low pressures. So we have another section talking about the pressure dependence. I think it's tomorrow's section. Bill will talk about that. So for here, there are 3 methods for calculating the rate for pressure dependence in RMG. And we usually recommend you to choose the modified strong collision. It's usually the most robust one. And for all the other, the chemically significant eigenvalues or the reservoir state, they are very expensive and not guaranteed to be very robust. And for the interpolation or the fitting rate, it would either be Chebyshev or P-log. And here is just one example that you will see from the campaign file if it's a PDAP reaction. So you will see the P-log at different pressure range, you will get different rates. So for the species constraints in the input file, you should always set allow, which is important to ensure that the species in your input file, which could be added to the model. And you can also specify the maximum radical electrons or maximum carbon atoms, oxygen atoms, or nitrogen atoms. And for the radical electrons, usually you can set it to be maximum of 2 radicals is sufficient for most systems, except for nitrogen, because nitrogen tri-radical is a notable exception. And for large pyrolysis models, we recommend you just set it to be 1, because you will already get a very large model. And the element limits should be carefully considered, because it depends on what type of chemistry you're expecting. For example, if you're expecting to have a lot of recombination reactions in your system, then you probably need to carefully calculate what's the maximum allowed carbon atoms after the oxygen atoms. Yeah. And like, for example, if your system has like, is mainly like cracking dominant, then you can like probably safely set the carbon atoms to be smaller value. And for the QMTP, it enables the on-the-fly quantum calculation using semi-empirical methods, which supports MOPAC and Gaussian in the software here. But it could be very slow compared to the group additivity method. And the group additivity accuracy has been improved largely. So you will not be considering QNTP because it might not worth the cost. And this QNTP you generally use only for stable cycloids and can be executed in parallel.
We didn't think that. I'll also say that MOPAC is now included with RMG. So I think previously, if any of you used it before, you had to go to the MOPAC website and get a license key because we were using an older version, but the modern version is open source and free. And it's prepackaged with RMG. So if you do want to use MOPAC, there are no extra steps. But as Yancy mentioned, there's some trade-offs in terms of speed. Please.
And we also have machine learning estimated thermal. So it's neural network thermochemistry estimator, and now using FinProp. It used the graph convolution to generate a multiple fingerprints. And it's trained on large set of quantum calculations, could be better than group additivity in some cases. And you can, as you can see here, you have many options to limit the types of the molecule, which would be estimated not from the group additivity, but from the machine learning estimator here. And we also have the surface reactor, which could be very useful if you have catalyst and can simulate a heterogeneous catalysis system. And we also have the RMG CAT session on Wednesday. So some recommendations, suggestions for picking the libraries and seed mechanisms. The thermal and kinetics libraries needs to be chosen very carefully. And if you are wondering what reactions or what species are included in different libraries, you can always go to the RMG website. So there's a visualized wall that can effectively help you to visualize what's the species and reactions included in different libraries. And which libraries you use can make a very large difference in your model results. So it's important to provide the kinetics library for kinetics that RMG cannot estimate properly. For example, the small molecule chemistry. And it's also important to provide the thermal and kinetics that are not fitted, because fitted thermal and kinetics often don't mix well with the RMG estimate. And here are some recommendation libraries that you can use for different kind of systems for oxidation or combustion of oxygenates. There are great thermal libraries. You can use the CODES10 2016 for the Berk H2O2, for the thermal DFT, CCSD, CBS53, DFT thermal. And for the seed mechanisms, we recommend to use the CODES10 2016. And you can also substitute the FFCM for the CODES10 2016 in seed mechanism, or the Berk H2O2 for in argon and helium or kinetics library instead of using this. And if you're using the FFCM kinetics, use the corresponding thermal library instead of the previous one. And it's worth noting that the remaining reaction libraries for larger species included with RMG or oxygenate things are fitted or their reactions have already been added as the RMG's training database. So they won't help with the new models. And for the nitrogen, we have some great thermal libraries. Also have some great kinetics libraries, which is called the primary nitrogen library, or the nitrogen and pozole. So we'll have I believe tomorrow's session will have more talk about the RMG database, and you can, if you have some good results, you can also like add it to the RMG database to help your kinetics simulation. And for sulfur, we have great thermal libraries showing here, and also for the kinetics libraries. But it depends on the application, and lots of the kinetics available in the sulfur folder in the RMG database. And if you're dealing with the aromatics, you can use the Sabic aromatics, which has a lot of great thermal calculations. And if you're looking for the kinetics library, you can use the first to second aromatic ring or the light sulfenzene. It includes some of the phenyl migration reactions.
So do these libraries have like a good, like sort of, I guess, the summary, like if I, for example, want to run a reaction, I go to like the RMG database or like the website. Can I have are there a few lines sort of describing like what this library might be important for and so on and so forth?
Yes, every file.
Okay.
So understanding the RMG output. So after you run the super minimal example, you will get a list of the folders that generated and some files. And if you look at the RMG.log, which is the primary log file for simulation, and it will basically like print out like all the warnings and the exceptions, error messages that you have during your model generation. So it could be useful if you like know what you're looking for. And it will basically shows the total history of how does the core being constructed. And you will see, sometimes you will see another log file, which is called the collision rate violators. It will list all the reaction which has the rate exceed the collision limit. And then if you see you have the collision rate violators log, it's better like you check the reactions listed in this file. And you will also see the restart from sig.py. It's basically the RMG input file that you can use if you would like to restart the model generation. And remember to set the generate sig for each iteration to be true from your original run, so that you will get the sig files, the sig folder. And for the mechanism files we're looking at, you can go to the Cantera folder or the Camping folder or the RNS folder, and the mechanism files will be located in different folders. And for the supplementary files, we can also like see for the sig directory, it will be the sig mechanisms. So if you click on that, you can see 3 subfolders. The one is the filter, which include the 3 arrays of the information, and the other one will be the sig, which is the core you have from your model, and the other will be the sig underscore age, which is the age file from your run. And for the PDEF directly, if you're running a pressure dependent network files, then there will be some files over there. Otherwise, it will be just blank. And for the solver directory, it will store the simulation profiles here. And it will include some plots if you like set it in the original input file to be true. And for the plot, yeah, you can look at some simulation statistics. For example, like how much memory it used for this simulation and how much time it costs like running one simulation and how many simulations it has been passed. And for the output.html plus species, like unless you set it in the input file that generate HTML to be true, or like otherwise you will not see those files and folders.
One quick question. You didn't mention the collision rate violators. So I'm assuming it's sort of the rate rules that end up giving, like rates that are higher than the collision rate. Would that be why you're getting those higher rates?
Yes.
And so does it stop the RMG run, or does it like sort of keep continuing by assuming that anything that's above the collision limit is just set to the collision limit? Like how does it deal with the rates that are higher than the collision rates?
So, yeah, that's a good question. I think the RMG run will still keep running. Yeah.
But does it take the higher rate or does it take the collision rate of these?
Do you have any experience?
What's the question?
So will if the reaction rate has exceed the collision limit, will the rate in this RMG run being modified to the collision limit, or it will still remain to be the estimated rate?
If I remember correctly, I think you will just keep the original number. However, you will get a file called inflation limit something and indicate which rates are in problematic.
But are you expected to sort of correct those rates or like force set it for the next simulation to be the collision? Because I'm assuming that if it's providing some sort of, I don't know, like really fast reaction, right, you probably just have the collision rate to be like the limiting rate there. Like, so what sort of the solution once you have, do you just restart it and then set those reaction rates to be the collision limit, or? Because I'm assuming
That's a
also,
good
yeah.
one. Yeah, we'll check and get back. to
Okay,
you.
okay.
Yeah, we're pretty much done. Thank you.